In this lecture, we are moving on to the module 2. Again, we are moving on to module 2. In module 2, we are moving on to the contents: well losses and well efficiency, well interference, and multiple well system. These are the topics which we are going to discuss today. Before moving on to the specified topic, we have to know some important terms related to well performance. First one is the static water level. Some of the terms which are related to the well and its performance we have to know. First one is the static water level. Static water, you can see the figure. So this is the static water level. It is the water level in the well, or water level in the well without pumping. If pumping is not there, then the water level in the well is known as static water level. It is the normal water level. Now, what is pumping water level? Pumping water level is the water level in the well when pumping is continuing. Okay, so this is the pumping water level. So it will be lesser than that of the static water level. Now, what is drawdown? It is the difference between the static water level and the pumping water level. It is the difference in level between the static water level and the pumping water level. When pumping occurs, the water level in the well decreases slightly. That decrease in the water level is known as drawdown. So this is the drawdown. Now, well yield per flow rate. Well yield or well flow rate. It is a volume of water per unit time discharged from the well. Example, in meter cube per day. How much is the amount of water discharged per day? Another term is specific capacity. Specific capacity is the yield per unit drawdown. Specific capacity means capacity of the well per drawdown. S is the drawdown. S is Q by S. S is the drawdown here. Now drawdown, we have already discussed what is drawdown. Now we will move on to another term, that is cone of depression. Cone of depression means while pumping occurs in well, the water level in the well and the surrounding areas form the shape of a cone. That cone is known as cone of depression. So here in this figure you can see that the static water level, this is the static water level, this is the pumping water level, and the in between area forms a shape of a cone, inverted cone. Okay, so that this cone is known as cone of depression. Now, area of influence. We can say that it is the outer limit of the cone of depression, area of influence. So, how much area is influenced by the discharge from this well? So, this well is discharging out. How much area surrounding the well is influenced by this discharge or pumping? It is known as area of influence. And radius of influence is the radial distance which is influenced by the pumping. Okay, or it can be we can say that it is the distance between the pumping water level and the radial distance between the pumping water level and the original static water level during pumping. So static and pumping. Okay, so these are the different terms which we have to know before moving on to the lecture. Now we'll move on to our first topic, well losses. So what do you mean by well losses? We have discussed about drawdown. Drawdown is the decrease in the water level during pumping. Okay, but the calculated drawdown, we can calculate the drawdown theoretically. Okay, by use of some graphs and all. The theoretical drawdown and the actual drawdown will be different. Okay, will be different. It will not be the same. Okay, that difference comes due to the losses in the well. Okay, in the well there may be some losses of water, some types of losses, head loss. Some head losses may occur in well. Due to that losses, the drawdown, theoretical and observed drawdown will be different. Okay, that losses is known as well losses. The well losses may be due to four reasons. Four different reasons are there. One is head loss resulting from laminar flow in the water bearing formation. So this is due to the formation. Formation means the type of soil in the well. There may be different types of soil. Okay, different types of soil in the ground. When water flows through each of this type of soil, there may be a loss in the head. Okay, loss of water in the head. So that loss is known as formation loss. That is one kind of loss which is included in the well losses. So these two combinedly known as well losses. First one is the formation loss. Second reason for the well losses, head loss resulting from turbulent flow in the zone close to the well face. So at the bottom of the well, just bottom of the well, the turbulent flow will occur. Okay, up to this point, the flow will be laminar. Now at this point, the flow will be turbulent because a pressure drop occurs here. Due to that, a high flow of water, that is a turbulent flow of water occurs. So there comes a head loss. That is another cause. The third cause of well loss is head loss through the well screen. Here there is a well screen, right? In which there are many pores. There are many holes in the well screen through which the water is filtered into the well. So when water flows through this hole also, there may be some head loss occurs. Okay. When water flows through small holes, a pressure drop occurs. A pressure drop occurs there. So that head loss. Another reason for well loss is head loss in well casing. Well casing means this is the well casing. So when water flows through this, there is another head loss. So these are the different causes by which well losses occurs. So it can be generally classified as formation loss and normal well loss. Okay. So these are the four reasons by which well losses occurs. So this is an illustration of this well loss. Now, normally, if there are no losses, the drawdown will be S1. Okay, S1 will be the drawdown. Due to these losses, what will happen? I am sorry, S2 will be the losses. S2 will be the drawdown. That is, that much of water will be taken out of the well. Due to this losses, what happens? The water may not be discharged much. Okay, Q may not be the discharge. Actually, the whatever is the water which we expect from the well, we will not get that much amount of water. So the drawdown will be lesser due to the losses. Okay, due to the head losses in the well. So this is the area of drawdown influenced by well. Now how can we express the well losses? So equation for the drawdown is normally given by the given as the sum of formation loss and well loss. We have already discussed about two types of losses in the well. One is the formation loss and the other one is the well loss. Well loss occurs due to three different reasons. Okay, while formation loss occurs due to one reason. So the total drawdown will be a sum of well loss and formation loss. Well loss is BQ, well loss is CQ square and formation loss is BQ, where B is the coefficient of formation loss and C is the coefficient of well losses due to 1, 2 and 3. 1, 2 and 3 are the reasons which we have discussed earlier. So this can be otherwise written as SW by Q is equal to B plus CQ, where SW is the drawdown, SW by Q is the specific drawdown, we can say. So this is the equation for well losses. Now how can we calculate this? When we are plotting a graph, between SW by Q and Q, this is specific drawdown and discharge. Specific drawdown and discharge. The graph will be like this. Okay. Now the slope of this graph will give you C. Slope of this graph will give you the C value. C is the coefficient of well loss. And the grade intercept of the specific drawdown axis will give you the value B. So this is the B. B is the formation loss coefficient. So when we are drawing, we have to draw a graph between specific drawdown and discharge. The graph will be like this, and the slope of this graph will give you the value of C, and the intercept on the specific drawdown part will give you the value of B. So like that we can calculate the well loss and well loss and formation loss. Now how can we demonstrate this well losses? We can demonstrate this in three different ways. Well loss is there, but how can we say that there is a well loss? What are the proof for that? So there are three different ways by which we can calculate. We can demonstrate the well loss. One is from the recovery immediately after pumping is stopped. Second way is from the distance drawdown curve if an observation well is available. So this method can be used only if there is an observation well available nearby our well. The third part is from the step drawdown test. So these are the three ways by which we can demonstrate the well loss. Now we'll move on to the first way, that is from the recovery immediately after pumping is stopped. So if we are pumping the well, okay, if we are pumping the well, we can see that there is a constant rate of drawdown. There is a constant rate of drawdown occurs in the well. But if we stop pumping, okay, there will be a cone of depression and a drawdown. We can observe that while during pumping. When we stop the pumping, what will happen is the recovery will be higher. Recovery of water, the cone will fills out, right? When we stop pumping, the cone of depression will get filled. Primarily, what happens is the filling of the cone will be rapid when we switch off the pumping. Okay, immediately after switching off the pumping, the filling will be rapid, and after some time it will be gradual. So from that we can say that there is a huge loss at the part. Okay, a huge well loss occurred. Okay, so we can say that for the first 1 to 5 minutes after pumping is stopped, there is a rapid recovery of water into the cone, after which the recovery pattern is normal. So from this we can say that there was a huge loss. Okay, that is one demonstration. The second way of demonstrating this well loss is from the distance drawdown curve if an observation well is available. So if a well is available and we are doing a pumping test in that well, now we can say that T is equal to 2.303 Q by 2 pi delta S is an equation for transmissivity. We have already discussed about this. So this is the equation for transmissivity of the well. Now here there is a delta S, that is the change in drawdown. The distance, if you are drawing a distance drawdown graph for the effective drawn or plotted and extrapolated towards the well at a distance of RE, the effective radius of the well. RE is the effective radius of the well, which is equal to the radius of the well plus the gravel pack. Okay, that is the effective radius of the well. So we are drawing a distance drawdown graph. Distance drawdown means radial distance. Distance to the observation well. Up to the observation well, we are taking different distances, and the drawdown at that particular pace we are measuring, and we are drawing a graph, and we are extrapolating this graph to the effective radius. Okay, normally it will be noticed that the observed drawdown is greater than the drawdown read from the graph. So the difference will give the well loss. This is another way to demonstrate the well loss. We are measuring the drawdown theoretically, and we are measuring the drawdown in the actual case. Now we are comparing these two drawdowns. There will be some differences. From that differences we can say that there is some losses. The third method is from a step drawdown test. Step drawdown test means we are carrying out the test at 3 to 5 different rate of pumping. Okay, we are calculating the drawdown at the same location for different time periods for different pumping rates. Okay, no, for same time periods at different pumping rates. For the first time we are taking the pumping rate of, we are taking drawdowns at 30 minutes interval, for example 30 minutes interval, and the pumping rate is constant. We are taking 50 liter per minute. Okay, that is the pumping rate. So at that rate we are taking 30-minute interval, and we are taking the reading of drawdown. That is one case. Now again we are repeating the same pumping with a pumping rate of 100 liter per minute. So like that many steps are followed, and the well loss coefficient C can be calculated as delta S2 divided by delta Q2 minus delta S1 divided by delta Q1 divided by delta Q1 plus delta Q2. That means delta S2 is the change in drawdown in the second case. Delta Q2 is the change in pumping. Okay, increase in pumping rate at each step. Delta S1 is again, so delta S1 and delta S2 values are given. Delta S is the difference in drawdown after completion of each step, and delta Q is the increase in pumping rate at each step. So from this value we can get the value of C. So if this may not be same. Okay, if there is no well losses, then this delta value should be same everywhere, but it is not same. So we'll get a value for C here. So from this we can say that there is a well loss. So these are the three demonstrations by which we can say that there is a well loss exists. Now we'll move on to another term, that is well efficiency. Well efficiency is nothing but it is the ratio of the actual specific drawdown, I mean specific discharge, to the theoretical specific discharge. Okay, I mean specific capacity, specific not discharge, specific capacity. This is the computed specific capacity compared with one measured specific capacity. So Q by SW is the measured specific capacity, and Q by BQ is the computed specific capacity. So we have already known these terms are known to you. BQ is the formation loss coefficient and all. So 100 into B by Q and Q got cancelled, and 100 into B by SW we can got as the efficiency of the well. It is the ratio of measured specific capacity and theoretical specific capacity. Now we are moving on to the another important thing, that is the well interference and multiple well system. In this figure you can see that there are three wells having discharge Q1, Q2 and Q3, but these three wells are placed at a close distance, okay, so that their cone of depressions will interfere with each other. So the cone of depression of this well is this one. It interferes the cone of depressions of this well. So the cone interferes here. The cone of depression of these two wells interferes at this point. So when there are many number of wells at the same place with interference in cone of depression, then that type of a system is known as multiple well system. In some cases there are several wells tapping the same aquifer and located within the radii of influence of the wells, which result in intersecting cones of depression. Then that is known as multiple well system. Okay. Now, when the cone of depressions of two or more nearby pumping wells overlap, the well is said to be interfere with one another. So we can say that here the wells are interfering with one another because their cones are intersecting each other. Now, how can we calculate this drawdown in this cone of, this types of wells? How can we calculate the drawdown? In case of confined aquifer, okay, the case of the well interference in case of confined aquifer, we can see first. In case of confined aquifer, the water is confined between two layers. You all know that. Okay, it is confined between two layers, upper layer and lower layer. So the thickness of the aquifer will be uniform. Okay, the thickness of aquifer will be constant because water will be filled in the entire thickness of the aquifer. Because, so that the transmissivity value will be same. Okay, it will not change with the space in case of confined aquifer. So in case of confined aquifer, we can say that the total drawdown will be equal to, if a number of wells are tapping this confined aquifer, the total drawdown from that particular aquifer will be equal to drawdown of well A, drawdown of well B, drawdown of well C, drawdown of well N. The sum of all these values will give the total drawdown. There are a number of wells A, B, C, D, etc. up to N. Then the drawdown of the aquifer, confined aquifer, will be equal to the sum of all the drawdowns in the wells. This is specifically for confined aquifer. Now we are moving on to the case of unconfined aquifer. So unconfined aquifer means it is not confined at the top portion. It is confined at the bottom only. So what will happen? It has different thicknesses. Okay, the thicknesses will vary. Some places there will be deep depressions. In some other places there will be heights will be there. So slope will change. Accordingly, the transmissivity value also will change for this unconfined aquifer. So the drawdown cannot be added up. Okay, since the thickness is not normal, since the transmissivity is not normal, we cannot add up the, if we are tapping more aquifer, more wells in that kind of aquifer, we cannot add up the drawdowns for getting the total drawdown as in the case of confined aquifer. So we have to follow certain steps in case of unconfined aquifer for finding the well interference in case of unconfined aquifer. So these are the different steps. The step one is we have to determine the theoretical confined drawdown. If the aquifer was a confined aquifer, then what will be the drawdown in each well? That we have to find first. Second thing is we have to sum up all the drawdowns. As in the case of confined aquifer, we have to sum up the drawdowns of each wells. Okay, as in the case of confined. The third step is we have to calculate a correction factor because it is not confined aquifer. This is unconfined aquifer. So we cannot exactly give the value of a confined. As in the case of confined aquifer, we cannot exactly sum up all the things. That is not the exact value. So we have to calculate the correction factor for confined, unconfined aquifer. So this is the correction factor. S is equal to H0 minus root of H0 square minus 2 S dash H0, where S dash is the drawdown in the equivalent confined aquifer. We have calculated in the step 2. Okay. S dash. S dash is the drawdown for an equivalent confined aquifer. H0 is the initial saturated thickness of the aquifer. The thickness will not be same in this case, but we are taking an average or initial thickness. So this is the correction factor. Now, the actual drawdown from all the wells in this aquifer will be equal to step 2 minus step 3. That is the drawdown which we have calculated here minus the drawdown which we have calculated here will give the actual drawdown of this well interference in the unconfined aquifer. There are many number of wells, then the total drawdown will be equal to step 2, drawdown in step 2 minus drawdown in step 3 in the case of unconfined aquifer. So these are the different things which we have to discuss. We have discussed in this, and there are certain applications for this well interference. It is very much helpful in case of drainage. If we have to do drainage, then well interference is a very good thing because much amount of water can be extracted out since the drawdown is higher. Now it is very helpful in the alignment of wells. These things you can read. So this is about today's lecture. Thank you.